So last time we introduced this Bose-Einstein condensation phenomena. Now we could formally enter a new chapter, which is phonons in solids. Okay, so phonons, as I mentioned earlier in this lecture, is made of harmonic vibrations of ions in the solids. Remember, those atoms or ions can actually vibrate at finite temperatures close to their equilibrium positions. And this kind of lattice vibration are kind of a many-body effect, because any lattice vibration in any position is going to couple to any other ions, okay, where all the other ions can also vibrate. So it's kind of a coupled harmonic oscillator problem, right? So imagine that, for simplicity, we could imagine that we attached a spring to a one-dimensional lattice, and each lattice point represents atoms or ions sitting on the lattice point, right? So that all these lattice points or ions are connected by a spring on adjacent sides, so that it is a coupled harmonic oscillator problem. So in quantum mechanics, for a single harmonic oscillator, you can solve this by defining this raising and lowering operator in quantum mechanics, so that you could solve these eigenstates and eigenvalues of a single harmonic oscillator in quantum mechanics. Here, we have a more complicated situation where we have not just one harmonic oscillator, but many. So there are many harmonic oscillators, but they are not independent, because, of course, the lattice vibration of any given site L will actually affect all the other lattice vibrations of all sites. Okay, so this is not an example of the collective motion. Later we'll see that this is kind of a normal mode vibration, that everybody affects everybody else. But still, we could sort of take advantage of what we learned in quantum mechanics to actually diagonalize this kind of complicated coupled harmonic oscillator, and we can find the normal mode vibration. And in that normal mode language, we could recognize that this has everything to do with the results that we already learned from the quantum mechanics, namely the single simple harmonic oscillator. So the coupled harmonic oscillator is nothing but a variation of a single simple harmonic oscillator that everybody should be familiar with. So we will derive such a relation in just a moment. So let me just remind you, this is kind of a harmonic potential existing in solids. Remember, this is the ion core sitting on the lattice site, but due to the ion-ion repulsive interaction, and also some kind of electron-ion attractive interaction, so there is a kind of a balance between attractive and repulsive interactions in the realistic solids, so that for ion, it's experience a kind of a harmonic trap in the potential energy. Okay, so this is the shape of this potential field by the ion. Okay, so you can imagine that this kind of a similar potential is actually periodic. Okay, and all the ions feel pretty much the same periodic potential, where there's a global minima inside the trap. So, of course, this shape of this potential may not be as simple as just a quadratic dispersed potential like the simple harmonic oscillator. So this is simple harmonic oscillator. Potential, which is quadratic in displacement, half of YL squared, or you know that v of x is nothing but 1/2 kx squared in quantum mechanics, right? Of course, the shape of this potential in a realistic solid state systems may not be as simple as this harmonic potential. Nevertheless, we could make approximations. Okay, so we could say, well, up to second order imperturbation theory, we could forget about the deviation from the harmonic potential, and we could simply just approximate this potential by the harmonic potential. Okay, in other words, we could Taylor expand this potential near this kind of a minimum point of this potential well, and we can Taylor expand this by assuming that the displacement YL is really small, tiny, so that we could Taylor expand this potential near this minimum point. Okay, so of course we get the zeroth order constant V0, which we don't care because this is just a constant shift. We don't care. And of course we get the first order derivative term where we know that this is going to be 0 because if we Taylor expand the potential near the bottom, which is the minimum point of this quadratic or quadratic-like potential, then the first order term simply just vanish because the slope of this curve at that bottom vanishes. So the remaining part consists of the second order term, which is the lowest order contributions to this kind of Taylor expansion theories. Okay, so the second order term consists of this quadratic in displacement YL times YL prime, where L and L prime are not necessarily the same, and times the second derivative's potential respect to this displacement variable YL and YL prime, and evaluate it near minimum point where YL and YL prime vanishes. Of course, this is just the second order contributions. We have the higher order or the third order contributions. Of course, we have fourth order and nth order contributions, which we neglected here at this point. Then later, we will come back to the third order cubic terms, which we call this n-harmonic term. So this n-harmonic term plays a crucial role to reach the thermal equilibrium for solids. But at this point, we don't need this higher order term higher than this quadratic in Y. So now we can simply just keep this potential or approximate the potential in terms of this quadratic expansion, and we can rewrite this harmonic potential in terms of this matrix product. Well, remember, this is a kind of a summation over all possible L and L prime sites with a different displacement YL and YL prime. So in the second derivative for this potential is respect to YL and YL prime, where L and L prime are not necessarily the same. Okay, and therefore this is a matrix form. Okay, so the results can be expressed in terms of a matrix product between, say, a row matrix, which is 1 by n, and n by n matrix elements, whereas VLL prime is nothing but the second derivative's potential respect to YL and YL prime, where L and L prime could be either 1, 2, 3, up to n, and same for L prime. So it is in general n by n matrix. And the last term is the column matrix, which is n by 1. So this tells us that you have a product of matrices among 1 by n and n by n and n by 1, which is nothing but a number, right? So then we could symbolically rewrite this kind of a summation over L and L prime, the second order term, in terms of the matrix product. Of course, based on the knowledge in classical mechanics that you could diagonalize this complicated n by n matrix and find the eigenvalue and eigenvectors, and the eigenvalue and eigenvectors, especially the eigenvectors, are simply just linear combinations of all different displacement vector YL in Fourier space. So we will derive such a normal mode later, but let's assume that we could find such a matrix T which can diagonalize this n by n matrix V, right? So using your knowledge in linear algebra and matrix diagonalization, we can assume that if exists such a matrix T, which is n by n matrix, such that this similarity transformations is made of the matrix product among matrix T and V in the middle and T inverse on the right. And if I make a matrix product for these three matrices, and at the end of the day, I could get a diagonalized matrix. So this is VQ1 up to VQn. So I don't know whether we can find such a T matrix or not, but let's assume we can find it. Of course, for any arbitrary n by n matrix, we guarantee that we could have such a matrix T which diagonalizes n by n matrix V. Okay, so suppose we could get this matrix T from our knowledge in linear algebra, then we can form a linear combinations of YL and also this matrix elements in this T matrix, so that we can form a normal mode variables YQ. And in that case, we could simply just rewrite this harmonic potential in a diagonalized basis, right? So imagine that we could insert the identity matrix, which is made of this unitary matrix T and T inverse, and we could insert this identity matrix everywhere, anywhere I want, and I just insert here and there, so that this identity matrix is expressed in terms of a T inverse times T. Okay, but I know what this is. So if I simply just circle this YL times T inverse, and this is nothing but normal mode variables, YQ. And this is YQ tilde, where with YQ tilde is just a Hermitian conjugate of YQ. And in the middle, we have this matrix product among the three matrices made of T on the left and the V in the middle and T inverse on the right. But what is this? Well, this is nothing but this diagonalized matrix that we assume right here, right? Suppose we assume the existence of such a T matrix which allows us to diagonalize this matrix n by n matrix V, and this is the result, which is a diagonalized matrix, and we can plug in this assumption right here. This is simply just a diagonalized matrix. Okay, so with a delta function, delta QQ prime, which means that the matrix elements are finite only along the diagonal directions and 0 on the other parts. Okay, so now we could just define this normal mode coordinates and diagonalize matrix elements, and we can rewrite this harmonic particle potential in terms of the normal mode variables. And because this displacement vector is a physical quantity which can be measured, right? Because this is just a length of this displacement, right? So it's a length scale, so it should be real. So this vector should be made of real numbers, and therefore this YL vector is the same as Y dagger L, and so that this YQ delta is actually the Hermitian conjugate of YQ. Okay, and for this unitary matrix, which can diagonalize this n by n matrix V, this T matrix inverse is actually defined by taking the transpose of this matrix element first and then put this complex conjugate on each of the matrix elements. So for example, this A, B, C, D, if I can show that this is a unitary matrix and T start Ji. So, we could first diagonalize this matrix and then find the normal mode variables, and we can re-express the harmonic potential in terms of the normal mode variables and diagonalize matrix, and the result is given here. So the harmonic potential could be re-expressed in terms of the simple harmonic-like normal mode variables. Of course, we notice some minor difference or important difference is that for a single simple harmonic oscillator, this harmonic potential is nothing but 1/2 kx squared, where we have simply just one variable, is x, right? But here we have many degrees of freedom, a normal mode, degrees of freedom, where q runs from say 1 to n, where n is the number of ions. So suppose we have 2 ions, and there should be 2 normal modes, and 3 ions, 3 normal modes, and n ions, we have n normal modes. And the realistic solids, we have an infinite number of ions, therefore we have infinite number of normal modes. And the harmonic potential is simply just a summation over all such normal modes simple harmonic-like potential. So you can consider this harmonic potential of a realistic phonon in solids is made of n normal modes, but each normal mode is nothing but harmonic oscillator. And of course, this k in a single simple harmonic oscillator, this prefactor in the Hooke's law, this k in this phonon case is not just a simple prefactor or constant, but it depends on q, because this matrix element is actually consisting of n values, and each value corresponds to each normal mode variables, q1 up to qn. So these matrix elements can be considered as just the constant in the Hooke's law, but we have infinite number of Hooke's constant, k1 up to kn. Okay, so let's finish this derivation of the phonon Hamiltonian. So we have just derived this potential energy term within this harmonic approximation, and so now we should look at the kinetic energy term. So the momentum operator in the real space representation is given by minus I bar d by dyl, but we know that we can transform this yl into the normal mode variables by using this this matrix T, which can diagonalize potential energy, right? Let's just do it this transformation, and after we have done that, we could define this corresponding momentum operator in Q space, or in the normal mode space. So P of Q is defined by minus H bar d by dy Q, which is simply just matrix element of T inverse or TQL, multiply by YL, you sum over L. So after such a identification of a momentum operator in the normal mode, variables, so we can rewrite the kinetic energy term. We can simply just replace PL and by PQ by a proper transformation with the help of this T matrix, right? So we can simply just rewrite this kinetic energy term by using the relation between the PL and PQ and the T matrix. I skipped some details. You could check that you could really get kinetic energy in this normal mode language with exactly the same form as the kinetic energy in the real space. So the T matrix is gone, but it is hidden in this PQ because of such a transformation. But once we have done that transformation, the kinetic energy term is having exactly the same form as in the real space. So it is also quadratic in PQ and PQ dagger. So now we can simply just plug in the kinetic energy and potential energy back to the Hamiltonian, and we can define this called normal mode frequency omega q by this this relation which linked to the diagonalized matrix element VQ, and we can define this momentum operator in the normal mode variables, and we can show this normal mode variables YQ and PQ satisfy exactly the same commutation relations for the ordinary quantum mechanics, meaning X and P, or YL and PL, and this is delta LL prime. So this is the homework. So you start from this ordinary commutation relations for X and P, and you can derive that in the normal mode variables, YQ and PQ also satisfy these commutation relations, exactly the same commutation relation satisfied by X and P. Okay, so this is a straightforward homework exercise. So afterwards, we can define bosonic variables AQ and AQ dagger, which is linear combinations of YQ and PQ in such a way with a prefactor square root of 1 over 2m h bar omega q. Suppose we can define such a AQ and AQ dagger, then we can show that AQ and AQ dagger satisfy this canonical commutation relation for bosons. So it satisfies this boson commutation relations, and this is another homework to derive it, to prove it. So after we define such a bosonic variables made of, say, normal mode operators YQ and PQ, we could show that the Hamiltonian of a single one-dimensional Phonon system could be simplified in such a way that this is nothing but a sum over simple single harmonic oscillator, but with the different normal modes. Okay, so you sum over all single simple harmonic oscillator with the different, say, normal mode degrees of freedom. And this is also another homework to really derive it. So you simply just plug in the definition of AQ and AQ dagger, or you could do the inverse transformations to get the expression of YQ and PQ in terms of AQ and AQ dagger, and you could simplify this kinetic energy and potential energy term, and at the end of the day, you should get this kind of a simple form, that this is nothing but a normal mode summation of a single simple harmonic oscillator. You sum over all contributions from different normal modes, but each normal mode is nothing but a single simple harmonic oscillator. Later, we will analyze the eigenvalues, eigenstates of such a normal mode summation of a single simple harmonic oscillator, which represents the phonon in say, solids. Okay, so let's call it a day, and we continue next Monday.